Hi, everyone. This is Quentin Anderson. I am the co-founder and chief operating officer of Granite River Labs, headquartered here in Santa Clara, California. It is right at 9 o'clock a.m. Pacific time, and I'm going to give everyone just one more minute to get logged in and get their speakers turned on, and we are going to start our webinar on PCI Express 5.0 and the road to PAM4. Okay, and we'll go ahead and get started. So first, I just want to thank everyone that is taking time out of your busy days here in this challenging time to spend time with us here today. I hope that this hour will be very informative and educational for everyone. And afterwards, we'll be sending out a survey and welcome your feedback. First, I want to introduce today's presenters. So we have a very distinguished panel today here for you. First is Hiroshi Goda-san, who is the high-speed and optical product manager and business development manager for Anritsu. Goda-san is based in the Dallas, Texas area and is an expert on signal integrity. Next we have Darren Gray, who is the engineering fellow of Granite River Labs here in our headquarters. And Darren has a wealth of experience in high-speed data applications, including PCI Express and others. And finally, Eugene Soshansky, who's our director of global engineering for Granite River Labs. Eugene also has a wealth of experience in high-speed applications, especially PCI Express. Eugene is also Granite River Labs' main liaison to the PCI SIG. Just a brief note on the companies that are sponsoring the webinar today. So Granite River Labs, my company, is a world leader in test services and automation solutions focused on connectivity and charging technologies. Headquartered here in Silicon Valley. We have 8 labs around the world, about 200 people. And we also, so we provide test services for PCI Express and other technologies. And we also partner very closely with Anritsu to develop their receiver test automation solutions for the Anritsu MP1900A pulse pattern generator and BERT. And those solutions, of course, include PCI Express 5.0 and others. Anritsu is a global leader in test and measurement solutions for wireless, optical, microwave RF, and digital. And this includes advanced solutions for 5G, M2M, IoT, and of course, high-speed serial data applications like PCI Express. So just a brief review of our agenda. We're going to kick off talking about the evolution of PCI Express as a technology and look at some of the challenges now in the latest generation PCIe Gen 5 at 32 gigatransfers. And then we're going to spend the bulk of the presentation then focused on testing. So we're going to provide an overview of base versus TIM, and then go through some of the specifics for transmitter and then receiver, including link EQ and jitter tolerance. And then finally, we're going to look ahead here to PCI Express 6.0, which is targeted for 64 gigatransfers using PAM4 modulation. And we'll have a few minutes at the end here for Q&A. Everyone should have a little button on your console where you can ask a question. So certainly we encourage everyone to do that, and we'll do our best to try to answer it. If we're not able to answer it live here in the webinar, I will do our best here to respond to you over email. Just a note here that the presentation is going to focus mainly on the PCI Express physical layer. And we will also be sending out to all the attendees a link to download the presentation deck, and also both Anritsu and GRL will be posting the presentation as well as the recorded version of the webinar onto our respective websites. And with that, I am going to turn things over here to Eugene Sashansky, Director of Global Engineering of GRL, who is going to talk about first the evolution of PCI Express. So Eugene, go ahead.
Thank you, Quentin. Good morning, good afternoon, everybody. So I'll be talking about evolution of PCI Express, and through the agenda, moving to the transmitter side of the PCI Express physical layer. So historically, everyone demands things to go faster. Software engineers complain that hardware is too slow, and hardware engineers complain that software takes too long to process or load. Regardless, everyone desires to have one unique interconnect for speed and for interoperability. Back in the beginning of 2000s, there was a 3GIO spec that developed, which later got renamed to PCI Express. So PCI Express, I think, officially was announced in 2002. So in today's day and age, PCI Express is considered to be one of the main interconnect standards. It exists in every computer architecture and enables infinite applications to be run on. So we can look that there's an automotive that actually is in development right now. There's a cloud, storage-based, enterprise servers, all of them running over PCI Express. So PCI Express has started at 2.5 gigatransfers per second, and with the growing demand, bandwidth doubles on average of 3 years. Today we are working on Gen 5, which is 32 gigatransfers per second, and already begun looking at Gen 6, which is 64 gigatransfers per second. So the initial Gen 1, 2.5 gigatransfers per second PCI Express has followed the NRZ type of modulation. That concept prevails up to Gen 5, 32 gigatransfers per second. Starting with PCI Express Gen 6, the PAM4 modulation has been adopted. The 8B, 10B encoding was only used with Gen 1 and Gen 2. The 128B, 132 encoding was adopted starting at Gen 3 at 8 gigatransfers per second to sustain bandwidth throughput. Another addition to Gen 6 that was never done before at PCI Express is the introduction of the FEC, which is a forward error correction. We will talk more about it when we get to the Gen 6 later in this presentation. Okay, so now let's look at some of the differences between Gen 4 and Gen 5 of PCI Express. So the key differences between those two specifications, besides doubling in bandwidth, are channel loss. So the channel loss has been increased from Gen 4 of 27-30 dB to about 34-37 dB loss. So the ref clock jitter got lowered from half picosecond RMS to about 0.15 picosecond RMS. The reference receiver CTLE changed from 2-pole to 4-pole with the respective gain changes. The reference DFE changed from 2-tap to 3-tap DFE, and minimum I width decreased from 18.75 picoseconds to about 9.375 picoseconds. However, the I height has stayed the same between Gen 4 to Gen 5 at 15 millivolts opening. Now, the BR has not changed. It still stays at 10 to the minus 12 bit error rate. And the I is closed for both 16 gigatransfers and 32 gigatransfers per second. So now let's look at some of the challenges going at NRZ 32 gigatransfer per second, which is Gen 5. So the channel loss has increased, as I already mentioned, up to about 36 dB at 16 gigahertz frequency, but the bit error rate stayed the same. So most industry standards above 30 gigatransfer per second choose PAM4 modulation, However, PCI Express decided to stay at NRZ. The post-equalization eye opening is 15 millivolts, and this is with the calibrated stresses of random jitter, sinusoidal jitter, ISI, various noises, and sinusoidal interference. So anytime you reach above 36 dB loss, you're supposed to introduce redrivers. And PCI Express actually is in the discussion of including retimers into the specification going forward. There are very little differences between Gen 4 and Gen 5. Compliance tests and overall channel configuration. Connector is backwards compatible between Gen 4 and Gen 5. However, Gen 5 has some improvements for the loss and reflection. Well, even though it looks simple enough, don't be tricked. It is difficult to design the PCI Express Gen 5 32 gigatransfers per second. So now let's look some of the terminologies in the PCI Express specification world. So PCI Express uses various terminologies for the specification definition. There is a base spec specification that provides electrical conformance testing at the silicon level. No official compliance program or test fixtures are available for base specification testing. However, there are a base calibration fixtures available for Gen 4 and Gen 5 specification. Those fixtures are only used to calibrate the worst receiver channel only, and for the testing of the base receiver channel. For the transmitter, you have to use your own evaluation board. So the CAM specification that clearly defines all requirements and enables end product to be certified by way of the PCI SIG integrators list. PCI SIG offers compliance test fixtures, test tools, and compliance program is governed by the compliance test specification, CTS. There are also M.2 and Q.2 specifications and potentially some other ones. They're all are sub-specification of the CAM, card electromechanical specification. So let's start looking at some of the differences in testing going from base to CAM. So one can say that base and CAM specifications are similar, but in reality, they are different. So the base specification measurements are done, the measurements are done at the different test points. Different tools and methodologies are used. Coverage differs too. So for the base specification, you're supposed to use the evaluation board, and the measurements are done at the bulk of the package of the silicon under test. For the post-processing, you're supposed to use a SysIm tool to be able to analyze the eye opening. For the CAM specification, there's an official program and official test fixtures available. The post-processing uses a SIG test tool to be able to analyze the eye opening. So a lot of customers that visit GRL always ask same question in different ways. Which specification should I be testing to? Well, it's an industry acceptance way of looking at it by saying that if you are a silicon provider, you have to test to the base specification. However, there could be some exceptions to the case. So if you're a silicon provider, you have to test to the base specification. But if your silicon is used in one defined application, you can actually test it to the CAM, considering that you will provide the CAM form factor of your PCB design. But if you have a final product that is designed to the card electromechanical specification and the form factor of the root complex or add-in card, you must test to the CAM specification only. So let's look a little bit over the transmitter test overview for Gen 5 to Gen 4 and Gen 5 going to Gen 6. So for the base specification, the evaluation board is required to be provided to perform the testing. So the replica channel that exists on evaluation board is used to de-embed the channel from the measurement to be able to bring the test points up to the silicon. So as you can see, even though it's a little bit small in the picture, the next slide will show a better representation of it. You can see that silicon under test is populated on the evaluation board. You may or may not have a ref clock, depends on the topology you choose, and the test points are at TP1. So by measuring the S parameter of the replica channel, when the measurement is performed, you de-embed the replica channel by bringing the measurement up to the silicon level, the balls of the package. The embedded, you may actually, during the measurement, you may include the S parameter of the package per PCI specification. So this picture kind of a show blow up of the test setup that you can see the replica channel, the evaluation board, the silicon under test, and the interconnectivity to the scope. So various measurement can be done at the base specification. As you can see, you can do the UI and the GRL measurement. You can do common mode voltage, full swing TX with the equalization, with the electrical idle sets, and a full swing. You can also perform the pseudo package loss measurement, differential peak of the entire signal for the TX voltage, and you can also measure the TX presets from P0 to P1. Now, looking at the CAM specification, as I already mentioned, PCI SIG provides the compliance test fixtures. I will talk a little bit more about it on the next slide to show you a better representation of those fixtures. But for the CAM specification, the methodology varies a bit from the base specification. You measure the signal at the connector, or actually the SMP breakouts on the test fixture, but all the measurements are brought at the connector level. So during the measurement, you embed the compliance channel as well as the pseudo package of the defined loss for the package in the specification. At the end, you get a closed eye. So the CTLE and DFE filters are applied at the scope level to bring the eye opening and perform the measurements. So I forgot to mention one little thing. So for the CAM specification, you can perform the parallel measurements. You can do the presets from P0 to P10, and as well as all of the transmitter measurements. So right here, you can look at the test fixtures. So on the top left corner, you can see there's two CLB boards, stands for compliance load boards. The reason why there are two of them, so you can provide the flexibility of being able to test all possible width or of the root port on a root complex system. So there's a by 4 and by 8, as well as by 1 and by 16. So that way you can actually measure and have flexibility of inserting the CLB into available root ports for testing. On the top right corner, you can see that there is a CBB board, stands for compliance base board. This board is designed to test the add-in cards. You have a ref clock, as well as you can inject your external clock for the receiver or PLL measurements. And on the bottom, you can see there's an ISI channel. So the ISI channel is designed starting from Gen 4 to be able to reach the required compliance loss for the transmitter as well as the receiver testing. So the reason why the ISI channel, the ISI board has so many channels is because each one is the increment of about half dB loss as you switch from one to another. So this slide kind of represents the CAM testing topology for the transmitter. So as I already mentioned, for Gen 4, the loss channel is up to 2730 dB. So the red numbers on the picture represent all of the losses to Gen 4 specification. Those that are marked in blue nodes are the proposed numbers going to the Gen 5. So you can see that the connector, PCIe connector for the add-in card, the loss has been increased from 0.7 dB to 1.5 dB. The package loss for the root complex has changed from 5 dB to 9 dB, and a proposal including the total fixture loss is about 27.5 dB. Now, going to the bottom picture, this is for the root complex testing per CAM specification. You can see that the package has been changed or increased from 3 dB loss to 4 dB loss, and overall ISI, including the test fixture loss, has been increased from 2 dB to 9.5 dB loss. So that pretty much concludes my portion of presentation, and I'm passing on to Goto-san. Goto-san, go ahead. Thank you.
Thank you very much, Eugene. Very nice summary of base spec, chem spec, and TX test. This is Mr. Goto with Anritsu. I'm going to present PCIe Gen 4 and Gen 5 receiver LEQ test from the very practical point of view, showing some test example and actual troubleshooting. Object of RX test is DUT, device under the test, needs to make link equalization training successfully under the specific stressed eye condition. The DUT needs to optimize the equalization preset and CTLE, and then needs to go to loopback status, and then make a BER test bar measurement, and bar must be less than 10 to the minus 12. This is a recipe of the stressed eye. You can see from 2.5G to 32G. So 2.5G is Gen 1, and 16G is Gen 4, 32G is Gen 5. Let's just focus on Gen 4 and Gen 5. Both spec launch voltage is 720 millivolt to 800 millivolt differential, and you can find the unit interval. The 32 gig Gen 5, the unit interval is only 31.25 picosecond, and the stressed eye width is less than 0.3 UI. 0.3 UI is 30% of 1 UI, 31.25 picosecond, which means eye width is less than 10 picosecond. And eye height is 15 millivolt peak to peak. Very small eye opening. And to achieve this, SJ, sinusoidal jitter, is used to narrow the eye width. For compliance test, 100 megahertz SJ is used, and this is the also final knob to adjust the eye width. And random noise is 0.5 picosecond RMS. So that means for 10 to the minus 12, that is 14 times of RMS. So 0.5 picosecond times 14 is 7 picosecond peak to peak. That is kind of a background noise, always constant. Then differential mode noise is 10 millivolt peak to peak. This DM is also the final knob to adjust eye opening, and DM is for eye height adjustment. Then common mode noise 150 millivolt peak to peak. This is a recipe of the stressed eye. There are 3 steps for receiver LEQ test. The first step is calibration to make a stressed eye. First, you need to characterize ISI board that Eugene showed the ISI board like a 27 dB loss to 30 dB loss. Then calibrate eye amplitude, preset, SJ, RJ, then DM, CM, and get a final eye opening. The target is, you can see the small table on the right top side. The eye height target is 13.5 millivolt to 16.5 millivolt, and eye width is very small 1 picosecond windows. This is a target, and you can see very small eye opening of the eye, but this eye is equalized eye by SIG test. So actual eye into the scope is completely closed. You don't see anything. But once you calibrate the eye, stressed eye, now hook up your DUT and make a link training. The DUT needs to make equalization and needs to go to loopback status through the recovery state. Then, once the DUT goes to loopback state, make a bar measurement. The bar measurement is only 63 seconds for Gen 4 and only 32 seconds for Gen 5. So calibration maybe takes half day, then actual measurement compliance test is less than 2 minutes. And once your DUT pass the criteria of 10 to the minus 12, now you can make a jitter tolerance test to see how much margin your DUT have. For make the calibration, real-time scope is required. Anritsu but 1900 can be matched with 3 major scope vendors' scope. It works with Keysight scope, Tektronix scope, and Recroy scope. And MOI, method of implementation, is available from SIG homepage. Anritsu, Keysight, Anritsu, Tektronix, Anritsu Recroy, all 3 combinations are golden test suite for Gen 4 and Gen 3. Once calibration is done, this is a typical block diagram of the actual test of receiver. So you do not need any external component. The Anritsu BAT has everything to inject all noise and stress. And it goes to ISI board, Gen 4 and Gen 5 in different board. Then go to compliance-based board to test the DUT. This is very important to make a stable and repeatable receiver test. The key is the return path. You need to minimize the loss and ISI of the return path to isolate the problem. Now you are testing the receiver, and in general, for the receiver test, the DUT gets looped back and retimes the pattern or signal, and signal is coming back to the error detector. To isolate the problem, that return path must be minimum contribution to the errors. And Anritsu 1900 error detector has 15 millivolt sensitivity with embedded clock data recovery. So the contribution of the error is a very, very minimum. So let's talk about the actual calibration process. So you only need this BER tester, compliance board, and scope for the calibration, scope for response time measurement, and then DUT. That's it. The calibration at TP2, stressed eye calibration, is the most time-consuming and difficult portion. And again, same recipe, and you need to achieve this very closed eye using SJ injection, RJ injection, DM, CM injection, then ISI board. So there is a CTS to describe the details. And also MOI of Anritsu is a very detailed step-by-step methodology of the measurement. But basically, you have to select the right ISI channel to give 27 dB to 30 dB insertion loss at Nyquist frequency, then calibrate SJ, RJ, DM, and CM. So it's not easy step, very time consuming. However, GRL has a very nice automated software to make this calibration very quickly and repeatably. Also, when you use Lecroy scope, Lecroy has an automation software to make this calibration automatically. So that automation makes your life very easy, and you can repeat the same measurement, like 3 months later, 5 months later, you want to repeat the test, it's give you a very repeatable test. Once calibration is done, now actual measurement. The DUT needs to make handshake and training done and goes to looped back. And it's but of course support Gen 3, Gen 4, and Gen 5 compliance pattern and link training. This is the GUI of BER tester, but for PCI Gen 5. Once the DUT goes to loop back, make a bar measurement. If you see no errors, your DUT pass, no problem. But in general, it's going to be difficult to get error-free. And then, for the troubleshooting, cursor can be changed manually. The cursor set must be done automatically under the stressed condition, but when you see errors like 10 to the minus 5 or 6, you can change the cursor setting to manual, and then you can change the cursor set combination manually. In this case, 48 full swing, and you can change manually, and you can immediately see what's the BER with this setting of cursor. But manual adjustment is difficult, so when you have a problem, and its BER tester has a function to make this auto cursor matrix scan. So BER tester make the change of combination of cursor. So in this case, 63 full swing, and you can see the BER, the green portion is no errors, error-free, and the yellow, orange, some errors, but okay, and red sync loss. This is a very convenient function to find, okay, which kind of preset and cursor is the best for your DUT. There are two new requirements for Gen 5 link equalization training. One is the third training sequence. For Gen 3, Gen 4, there are two training sequences. One is through the recovery, the other one is just for the configuration. The third TS is added to Gen 5. The second new requirement is a pre-coding. So let me talk about the details of these two. The left side is a new TS training sequence. The center is the common and mandatory state. So the DUT must go to loop back through the recovery state. But when you have any problem, you can force the DUT to be looped back through the configuration. Gen 3, Gen 4, middle one and right one is the two TS. But Gen 5, new TS is added. So you can force the DUT in the loopback condition, but the DUT makes some equalization training. So just bypass Gen 4 and below lower frequency, but Gen 5 make a training. That this is the new TS for Gen 5. And also the pre-coding. The 32 kilobit per second is a very fast high frequency. So the receiver has DFE, but the DFE, because of the nature of the DFE, when the clock pattern of 101010 comes, and when the 1 bit of the clock pattern is wrong, that generates burst errors because of the nature of the DFE. There are a lot of white papers about this, but anyway, to avoid that kind of burst errors, to avoid 1010 clock pattern, you can pre-code the pattern to avoid this burst error caused by DFE. This is not a mandatory, so it's option. So you can pre-code the pattern, but you don't have to. Then troubleshooting of link training. The BER tester has LTSSM log viewer, link training status machine, and that LTSSM tells you very detail of the handshake. So you can see what is the problem or what kind of problem happened in the training sequence. And moreover, you can use you can specify the event of LTSSM to generate a trigger to your scope. And that trigger function, you can see the problem on the viewer, and then you can capture the waveform using that trigger. So you can make a troubleshooting from the digital information, and also you can make a troubleshoot from the analog point of view from the scope information. This is the detail, but it's very small to see. I'm so sorry, but you can see the timestamp of the event and also duration time of each handshake, and you can see bitrate and what the BER tester request and what's the response the DUT make. So that kind of handshake details you can see from this LTSSM viewer. So let's talk about the actual problem. So now from LTSSM, now you find the link never go up to 5G, always 2.5G Gen 1. So detect and polling, it's just a repeating and loop. What's the problem? But in this case, in general, signal is not coming to your DUT or from your DUT. So first, please reset your DUT. Maybe power reboot is required. And then if it doesn't help, maybe the connection is wrong. When you have 2.5G link failure, connection is wrong. Or 100 megahertz left clock is missing. So check 100 megahertz clock, then make sure the connection or cabling is correct. Some DUT needs to change the polarity of data and data bar. Now, speed change failure. Now, 2.5G and 5G, 8G, but it doesn't go to the next 16G, Gen 4. In this case, one of the problem was, so this is the TS. So through the configuration, it never goes to L0, so recovery state coming back to configuration and go back to the detect. In this case, one of the problem was the response time. the speed change must be done within 12 milliseconds for Gen 4 add-in card and 24 milliseconds for host. And DUT meet this specification, but spec is 12 milliseconds, so you have to wait 12 milliseconds. But some DUT, if the DUT change the speed like very quickly 1 millisecond, you do not wait. And if you do not wait, it times out, then it doesn't go to the next step. So please check. And to test this, you can set a different speed change waiting time, fast, middle, and slow. Then now loopback is okay, but you see some errors 10 to the minus 5, 6, 7. In that case, the major contribution of the loss is ISI loss. So please just reduce the loss of the ISI channel and you may see no errors. So then turn off the DM. In the practical world, RJ, SJ is not so major contribution. So just reduce the loss of ISI and see if your DUT get error-free. Once your DUT get error-free, now you can measure the tolerance. And Anritsu has a automated jitter tolerance test. For the jitter tolerance test, also Anritsu recommend giving a crosstalk effect. At Gen 4 and Gen 5, crosstalk is quite significant at the connectors. And Gen 5 spec, you may need to use other channel to give aggressors, but it's not easy. Some DUT only has one channel. So Anritsu recommend to configure Anritsu to have second pulse pattern generator PPG, and that second PPG can be aggressors for the crosstalk. You can change the pattern. You can set any patterns. For example, clock pattern 1010 is the highest frequency, so that is the most stressful pattern, and you can change the amplitude. So to make the worst case scenario, and it strongly recommend using second PPG for the aggressors. And then this is a test example of the jitter tolerance. Green light of the table or graph is the mask, and you can set how much the maximum jitter injected to see the margin. In this case, 100% margin. So from the mask, 2 times of the mask is the maximum, and see if the DUT has 100% margin. The last test is a TX link EQ response time measurement. The BR tester tells the DUT, hey, please change the preset, and scope measures how quickly your DUT can change the preset. This is the test example. So this timing, BR tester tells the DUT, hey, change the preset. Then actual change happened. This you can see the different preset. So now this time must be less than 500 nanoseconds. Okay, that is the overview of receiver test. Darren, it's yours now.
Okay, well, thank you, Eugene and Gochu, for your presentation. A lot of really good information there on PCI Express Gen 5. I wanted to continue our presentation by looking forward a bit to the upcoming PCIe Gen 6, which transition from NRZ or a non-return to zero to PAM4 or pulse amplitude modulation. I will briefly touch on some design and test consideration for this higher data rate and newer modulation format that will be used for PCIe Gen 6. So just stepping back, why the need for PAM4? Why not just continue with NRZ, which had been the case from Gen 1 through Gen 5? Well, as you probably know, in a really simplified way, a channel or an electrical path can be seen as a low-pass filter, as you can see on the right-hand side here. And obviously, as the frequency increases, the insertion loss also increases. And looking at this channel that we have displayed here on the snapshot here, you can see the insertion loss at Nyquist increases significantly from 28 gigabytes per second, 28 gigabits per second to 56 gigabits per second. And given the aggressive push to higher data rates by the PCI SIG as seen in previous slide, insertion loss becomes more and more of a challenge to compensate for. There are many techniques to compensate for this low-pass filter, and one of those techniques to be used by Gen 6 is PAM4. PCIe Gen 6 using PAM4 modulation was announced in 2019 by the PCI SIG. Gen 6 will include forward error correction or FEC as an additional technique for suppressing errors. It will also, which is really critical, maintain backwards capability with all previous generations of PCI Express. So that means all the way from PCIe Gen 6 back to PCIe Gen 5. And another important feature of Gen 6 is that it should deliver the same channel reach similar to what is currently used today on Gen 5. And just a brief introduction. To PAM4. PAM4 basically maps 2 bits onto one symbol. Typically, PAM4 will have 4 levels, and each level represents 2 bits. So basically, you can now transfer data at 32 gigabytes per second, but now sending 2 bits instead of 1. And if you look at the snapshot that's on the right side of the screen, this is intended to show that. If you look at NRZ at the top there, every 2, so you have initially 1, 0. Every 2 bits of NRZ is encoded in a PAM4 level for each bit. So each PAM4 level just refers to 2 bits for NRZ. And just to note that PAM4 is not a new modulation scheme. It is widely used for data rates above 25 gig for other high-speed standards. In fact, many standards transition to PAM4 for data rates above 25 gigabits per second. And PCIe is now following basically a similar path. So just in summary, for the same symbol rated Gen 5 at 32 gigabytes per second, you can get 2 bits transferred instead of 1. So this is all really good, and basically, I guess we're home free now for PCIe Gen 6. But there are some challenges that, and some challenges to transitioning to PCIe Gen 6. We have listed here a not exhaustive list of topics that would be of interest as we move to Gen 6. Just looking at the list here, reduced signal-to-noise ratio, increased susceptibility to crosstalk, backwards compatibility to Gen 1. These are all just some of the topics that we will briefly explore in some of in the next slide, just discussing the transition to PCIe Gen 6. Okay. One of the most important points that I hope to get across concerning the transition to PAM4 signaling is the cost and signal-to-noise ratio. As you can see in the comparison of the NRZI on the left-hand side versus the PAM4 signal with the 3 inner eyes, you can see that the inner eyes are actually reduced by up to 66% compared to the NRZ eyes. And this reduction in eye amplitude will tend to decrease signal-to-noise ratio for each of the eyes in the system if the system noise remains the same. So in summary, yes, you can transmit 2-bit with PAM4, but a price that's typically paid is that you have reduced signal-to-noise ratio, which you can clearly see by the reduced eye openings that you have for the 3 different eyes for PAM4. In addition to that, adding crosstalk, where near-in crosstalk, far-in crosstalk, integrated crosstalk noise to the mix will also become more of a concern with the reduced eye signals that we saw in the previous slide. And crosstalk can be a substantial contributor of jitter at the receiver, especially at smaller eye openings. Okay. And just looking at some of the other additional features of PAM4 Gen 6, there is the introduction of forward error correction, or FEC, which allows correction of errors at the receiver. Obviously, this requires additional overhead and symbols sent to allow the receiver to decode the errors correctly. This can increase latency through the link, and how much latency will be tolerable for Gen 6 will be determined in the future. In other standards, FEC can improve the BER from 1e to the -4 or 1e to the -5 up to 1e to the -12 or better. But despite the increase in latency that FEC actually offers, FEC will be needed to increase the BER for Gen 6 through the link. And just a word about also backward compatibility. The goal for Gen 6 is to maintain backward compatibility back to PCIe Gen 1 at 2.5 gigabits per second. This implies that a PCIe DUT may need to support NRZ at 2.5 up to PAM4 at 32 gigabaud per second, which is a fairly large range of data rate with 2 different modulation formats. And this is going to be quite of a challenge, not only for Gen 6, but for actually future upcoming PCIe data rates also. And finally, with the next 2 slides, I wanted to briefly explore a proposed equalization methodology for equalizing the Gen 6 link through approximately 32 dB of loss at Nyquist. Here you see a proposal of a 4-tap FIR filter on the transmitter, and improve CTLA and up to 16 taps of DSE. This is quite different from PCI Express Gen 5, especially in the increase in the number of DSE from 3 on Gen 5 to potentially 16 on Gen 6. And additionally, there's an additional tap on the TX FIR filter, from going from 3 on Gen 5 to 4 on Gen 6. But the takeaway I wanted to just to make sure you notice is that achieving successful error-free link, through a 32 dB channel will be quite challenging, and will likely require increased DSEs, CTLEs, and increased FIR filters, in addition to FEC for error-free operation. Increased complexity of equalization will definitely be required for Gen 6. And just one other slide, just indicating that that point. Here's a slide with some preliminary results using increased DSE 16 here and enhanced CTLE on Gen 6. And as you can see, looking at the left 2 columns indicate the center eye using Rev version 0.05 of the spec, and then to the right of that, on the second column, is Rev version 0.07 with increased DSEs, the CPEs, and TXDQs. And you can see some improvement in the eye height and eye width, but clearly even with dramatic increases in equalization, the eye height and eye width is not as pronounced as the increase in DSEs and FIR filters would tend to indicate. The takeaway from this is that PAM4 through a very lofty channel with 32 dB at Nyquist, which is very challenging and likely require additional DFEs, FERC filters, CTLEs, which is basically increases the complexity, power consumption, and basically a host of other factors. And just one final slide, this is basically food for thought for, hopefully the other slide comes up. This is just food for thought for potentially, I don't know if the other slide came up, but just some food. The last slide just was actually referring to some food for thought for just some things to think about. Okay, there it is. Just some things for questions looking at PCIe Gen 6 and also future PCI Express. Backward compatibility, will that continue in later versions of PCI Express? So that would be something that would be definitely going to be on the PCI 6 mind to actually determine, backward compatibility. And then there are several different questions also that, just food for thought for the future of PCI Express. I think that
okay,
was...
Darren, thank you very much. I really appreciate everyone hanging in here. I noticed that we had a few folks, I think, that had some audio and visual issues. I just want to, again, remind everyone that we will send the presentation and a link to the recorded webinar out here afterwards. So we've got just a little bit of time here for some Q&A. So I'm going to quickly go through a few of the questions that popped up. There was a question if the chem spec is available now for Gen 4 and Gen 5. So the answer there is that for Gen 4, yes, the chem spec has been published. For Gen 5, the chem spec is still in draft. So the Gen 5 base spec was released, but the Gen 5 chem spec still in draft. We had another question if Gen 4 and Gen 5 use the same, for the chem spec testing, if they'll use the same compliance baseboard, compliance load board, and ISI, so basically the fixtures. The answer there is no. So they will be using different fixtures, and again, those are under development for Gen 5, but still already available for Gen 4. And those fixtures can be ordered directly from the PCI SIG. In fact, that's really the only place that you can order the official fixtures for chem spec testing, and you need to be a member of the PCI SIG. We had another question, can I use a tunable ISI channel for the link EQ test? And Goto-san, I'm going to let you address that one. Go ahead.
Tunable ISI is very convenient to adjust the ISI, but I just recommend using the combination of actual ISI board plus the function of tunable ISI, mainly because one is a return loss. The digital ISI or tunable ISI can simulate the loss quite good, but the reflection characteristics is different. So using a real channel, you have a real return loss. The second one is the digital ISI can control the loss up to Nyquist frequency, but it doesn't control the higher frequency above the Nyquist. So using a real channel, you have a very good roll-off at the higher frequency. And then using a tunable ISI function to adjust, to make a fine-tuning. That is Anritsu's recommendation. Thank you, Quentin.
Okay, yeah, Goto-san, thank you. So just one more real quickly. We had a question about how do you measure the package, and I believe that, this spec this question would relate back to the base specification. So the short answer to that is that if you're using the base spec, accepted methodology for testing involves using a tool called CSIM, which is a statistical simulator tool that Eugene mentioned. And that tool has incorporated into it the package loss model and the other chip parasitics, and basically incorporates those parameters into the measurement. So what you get is, for a transmitter test, you get a post-process waveform that has incorporated the package loss and other parasitics through CSIM. When you're calibrating for your receiver test to the base spec, again, you're trying to de-embed the channel or calibrate through the channel so that you're calibrating a stressed eye as it'll be presented at the pins of the chip. And again, you use CSIM to calibrate that eye. And again, CSIM will incorporate in the parasitics around the receiver pins into that stressed eye, so that what you calibrate with your scope using CSIM along with your ISI channel and the stresses you put on your BERT is going to be essentially what will be presented at the pins of the receiver after it goes through your channel. So that was a good question. With that, I think we're out of time, and again, I really appreciate everyone taking the time out here. Here's our contact information. Again, we'll send this out over email, and I want to thank our presenters. And with that, we'll call it a day. Thanks, everyone. Stay well and stay safe.
Thank you very much.
Thank you.